Welcome back to the Deep Dive. Today we're plunging into the invisible world that quietly powers so much of our digital lives. Databases. You interact with them constantly, right? Whether you're shopping online, checking your bank account, maybe streaming a movie, or even just scrolling social media. Every single one of those actions involves a database working furiously in the background. But how do these massive digital libraries actually work? And what happens when a new technology comes along that completely reshapes the rules of the game? Our mission today is to take a deep dive into exactly that. We're going to unpack a stack of fascinating insights about how modern database technology, specifically SAP HANA, achieves, well, unprecedented speed and efficiency. We're going to understand the fundamental differences between, say, traditional data storage and this cutting-edge in-memory approach that's causing a genuine revolution. You might think databases are purely technical, maybe a bit dry, but by the end of this, you'll see how rethinking data storage can fundamentally transform a company's entire cost-benefit analysis. It's actually pretty exciting stuff.
Indeed. Today, we'll peel back the layers to reveal not just what an in-memory database like HANA is, but more importantly, why it represents such a significant leap forward. We'll explore the ingenious hardware and software innovations that have convinced major organizations, from small startups all the way to global enterprises, to fundamentally change how they handle their most critical information. It's really about giving them a competitive edge through, real-time insights.
Okay, so let's start with the basics then. When we talk about a database in this context, what exactly are we referring to? Is it simply like saving files on your computer's hard drive? Creating a new folder for your tax documents or photos, that sort of thing?
That's a great starting point, actually, because it highlights a common misconception. A database, at its core, it isn't just a random collection of files or a simple folder system. It's defined as a specialized software application. It's designed specifically to manage data in a highly structured, organized, and crucially secure manner. Its primary purposes, the non-negotiables, are enabling extremely fast retrieval and equally fast insertion of data, all while maintaining organization and providing robust security. Think of it less like a messy attic where you just throw everything, and maybe more like a meticulously organized digital library, complete with a professional librarian who knows exactly where every single piece of information is located, instantly.
Right, so it's far more than just a folder system on your computer's C drive or D drive. It's active software that actually manages the data, not just, stores it passively. And we hear about specific database software names all the time, don't we? Things like Oracle, MaxDB, SQL Database, SAP HANA, and Space. These are the powerful tools businesses really rely on every single second of every day.
Precisely. And this raises a really crucial question. Why can't a large corporation just save all its business data onto a massive server hard disk and, call it a day? Why isn't your external hard drive, maybe packed with hundreds of thousands of photos and documents, considered a database in this critical business sense?
Yeah, exactly. I mean, I've got a massive external drive. It's full of practically everything I've ever created.
Right.
It's organized to me, maybe by date or project.
Right.
Why isn't that sufficient for, say, a huge multinational bank?
Well, the critical disadvantages of what we call file system storage, which basically means just saving files directly to your operating system's drives, they become immediately apparent when you're dealing with the vast dynamic amounts of data a business generates. Just imagine a hard drive with millions, maybe billions, of customer records, sales transactions, inventory updates. If you're looking for, let's say, the 10,000th sales transaction from last year, a traditional file system often has to perform what's called a sequential read. This means it literally starts from the first file and reads through each file one by one until it hopefully stumbles upon the one you actually need.
Wow.
For large data sets, this isn't just slow, it's paralyzingly inefficient. It's like having to read every single page of an encyclopedia just to find one specific fact.
So if a customer calls my e-commerce business asking about an order from 6 months ago, my system might potentially have to scan through millions of orders just to find that one specific transaction. That sounds like a complete customer service nightmare and a massive drain on resources.
It absolutely is. And beyond that sequential read problem, file system storage just fundamentally lacks the structured organization that's specifically designed for quick access and, importantly, complex querying. Your personal photos might be in folders by year, sure. But what if you want all photos of, say, Aunt Carol and taken in 2022 and tag beach vacation? A simple file system struggles immensely with that kind of sophisticated instant query across different data points. And even more critically, Traditional file systems lack built-in security mechanisms to control who sees what data at a granular level, or robust recovery mechanisms to ensure data integrity if there's corruption or a power loss or a system failure. For business-critical data, these are just non-negotiable.
Okay, so database software, even though it's installed on your hard disk, just like a regular program, is doing something fundamentally different. It's not just sitting there, it's actively structuring and managing things.
Exactly. When you install database software onto your hard disk, it's not just passively occupying space. It essentially takes ownership of certain sections, creating its own meticulously structured internal world. What we sometimes call logical boundaries. It's kind of like building a custom, highly organized library inside a general warehouse space. Within these boundaries, the database software dictates exactly where every piece of data goes. It organizes it into highly structured tables, with rows and columns, much like a spreadsheet. But here's the truly crucial part. It creates and maintains indexes.
Ah, okay, like the index at the back of a textbook. That makes sense.
Precisely that. Think of an index just like the comprehensive index at the back of a large reference book. If you want to find information on, say, quantum physics, you don't flip through every single page, right? You go to the index, find quantum physics, see it's on page 247, and you go directly to that page. Without an index, you'd be flipping every single page, which is basically that slow sequential read we were just talking about. This indexing allows databases to retrieve exact data pointers almost instantly, dramatically speeding up access. It transforms searching from, well, a marathon into a sprint.
That's a perfect analogy. And it means that if you, the listener, were to install database software on your personal external hard drive, maybe to organize that massive photo collection you have, and then used it to create specific tags for each photo, like family, vacation, 2023, beach, allowing instant complex searches and retrieval based on those tags. Then it would start to behave like a true database. It's all about that active, intelligent management organization and that quick retrieval.
Absolutely. And that software would also provide mechanisms for atomicity, consistency, isolation, and durability, the famous AC properties you hear about. These are absolutely foundational for reliable business data. For instance, if you're transferring money between bank accounts, you need the transaction to be atomic, meaning either it all happens or none of it does. It needs to be consistent, so data integrity is maintained. Isolated, so other transactions don't interfere. And durable, meaning once confirmed, the change is permanent, even if the system crashes right after.
Right.
File systems just don't offer that level of inherent data integrity, not built in.
Okay, so we understand why businesses use databases instead of just dumping files. That structured organization, the indexing, those ACD properties, they make a monumental difference.
Yeah.
But even with perfectly organized data, how do computers actually get to that data super fast?
There's a whole complex hierarchy involved, isn't there, in how a computer accesses information. It's not just like a direct line to the hard drive. That's right. And to truly appreciate the revolutionary speed of modern databases, especially something like HANA, we really need to understand the computer's internal data access hierarchy. When your computer's processor needs data, it doesn't just go straight to the hard disk. It follows a very specific tiered path. It starts with the fastest and smallest memory locations and only moves to slower, larger ones if the data isn't found there first. Think of it maybe as a series of increasingly larger but progressively slower rooms where information might be stored.
So it's like a VIP lounge for the most frequently used data, then maybe a slightly larger, less exclusive lounge, and so on down the line.
Precisely. A good analogy. At the very top, closest to the processor, you have the processor caches. These are tiny, incredibly fast temporary storage areas physically built directly onto the CPU chip itself. You've got L1 cache, which might be around, say, 320 KB, then L2 cache, perhaps 5 millibit, and L3 cache, maybe 8 millibit. These caches, their access time is measured in nanoseconds, literally billions of a second.
Wow, tiny but fast.
Extremely fast. They're so small you couldn't even store a single high-resolution photo on them, really. But they hold the data the processor is most likely to need next, trying to anticipate its requirements.
And if the data isn't in those tiny, super fast caches, where does it look next?
Then the system checks the next level down, RAM, or random access memory. This is your computer's main working memory, often just called physical memory. RAM is significantly faster than a hard disk. We're talking tens of nanoseconds for access, mainly because it allows random access. This means it can directly pick any piece of data without having to read through preceding data sequentially. If you need the 8th piece of information, RAM goes straight to it. Unlike a hard disk that has to physically spin to the right spot, This is where your operating system, your active applications, and your currently processed data all reside.
Okay, so RAM is the fast, active workspace. But what if the data still isn't in RAM? Where does it go then?
That's when it finally goes down to the hard disk drive. This is the primary long-term storage, the vast digital archive where all your programs, files, and importantly for our discussion, most of your traditional database data are stored. Accessing data from a hard disk drive is measured in milliseconds. That's thousands, maybe tens of thousands of times slower than RAM. It's definitely the slowest of the bunch, primarily designed for persistent storage, not lightning-fast operational access.
This inherent speed hierarchy, it raises an absolutely critical question about database efficiency, doesn't it? These concepts of hit and miss hit, because that's what truly determines how fast you actually get your data back, right?
Absolutely crucial for understanding database performance. A hit occurs when the requested data is found right there in RAM, or even better, in one of the processor's caches. If the data is right there, it can be accessed almost instantaneously, allowing the CPU to just keep working without any delay. This is what you always want. You want to maximize your hits. A mishit, on the other hand, that's when the requested data is not found in RAM. This forces the system to go all the way down that hierarchy to the much slower hard disk to retrieve it.
Can you give us a concrete example? Like, how does this play out in real time for a business application, say that e-commerce site again?
Okay, sure. Imagine your e-commerce system needs to retrieve a specific customer's order history. First, the processor checks the L1 cache. Not there. It checks L2, then L3.
Yeah.
Still not found in any of those tiny, fast caches. Okay, then it moves to RAM. Now, if that specific order history data is not in RAM, that's your mishit. This means the system must then instruct the hard disk to locate that data. And once it's found, that data has to be loaded from the slow hard disk into RAM before it can even be processed by the CPU. This loading time for a mishit is significant. You cannot directly read or process data straight from the hard disk. It absolutely must first be brought into RAM to be usable by the processor. If you're seeing an image on your screen right now or a report is being generated on your work computer, it's because that underlying data has been successfully loaded into RAM. If it's not in RAM, you won't see it and the report simply won't be ready.
So to connect this back to you, the listener, imagine you're a busy sales manager and you need a specific report on last quarter's sales trends for a client call that's happening, like right now. A hit is like finding that report already open on your computer screen, ready to go. You just glance at it. Done. A mishit is realizing the report isn't on your screen or even in your recently opened files. It's buried somewhere in an archive on a slow network drive or maybe even on an old backup tape somewhere. You then have to initiate a request to retrieve that data, wait for it to be pulled from that slow storage, load it into your system's active memory, and then finally appear on your screen. That entire retrieval and transfer process, that's your mishit latency. And for a business where every second counts in a competitive market, constantly doing that adds up. It means lost productivity, frustrated customers, maybe even missed opportunities.
Exactly. When you're dealing with potentially hundreds of thousands or even millions of data requests per second in a large system, those seemingly small delays for individual mishits become monumental bottlenecks. They can grind business processes almost to a halt.
So, okay, if RAM is so much faster and these mishits are such a performance killer, why didn't traditional databases just store everything there? What were the limitations? It seems like the obvious solution would have been just to buy more RAM for your servers back then.
This is precisely where the traditional database dilemma comes into sharp focus. In conventional database setups, think of your long-standing Oracle or MaxDB or SQL Server databases. While the database software itself is installed on the hard disk, the crucial point is that most of the actual business data also resides predominantly on that hard disk. RAM acts primarily as a temporary buffer or cache. It holds only the actively used data or maybe data that the system cleverly anticipates will be needed very soon. It's not where the entire data set lives persistently, and it's not where all the primary operations are performed from.
So even if I had, say, a pretty high-end server back then with 256 gigabytes of RAM, which sounds like a lot, but my total business data was maybe 1 TB, which is 124 gigabytes.
Exactly. Only a relatively small fraction of that total 1 TB of data could physically fit into your 256 gigabits of RAM at any one time. This fundamental limitation means that traditional databases frequently, almost constantly, experienced mishits. Data had to be constantly swapped in from the slower hard disk into RAM when it was needed, and then swapped out from RAM back to the hard disk to make space for new, actively used data. This continuous swapping significantly impacts performance and leads to a perpetually lower hit ratio. You might only achieve a hit ratio of around, say, 70%. That means a full 30% of your data requests are incurring that expensive latency, that penalty of going all the way down to that slow hard disk.
And that means your CPU, the brain of the operation, is often just sitting there idle, waiting for data to arrive from the disk instead of actually processing it.
Precisely, it's a huge waste of processing potential.
What's really fascinating here is the stark cost-performance trade-off that businesses historically face with these traditional systems. It really sounds like they inevitably hit a wall where just throwing more money at the problem, buying more RAM, didn't yield proportional gains.
They absolutely did, and it was a significant source of frustration for IT departments and honestly a constant drag on actual business operations. Let's look at the numbers and the business implications, because that really tells the story. For a traditional setup, maybe with that 256 gigabytes of RAM handling 1 TB of data primarily stored on a hard disk, the hardware cost might have been around, let's say, $3,000 to $4,000 back then. And with that configuration, a complex business query, perhaps generating a comprehensive sales report, might take an average response time of approximately 30 seconds.
30 seconds, which feels like an eternity if you're waiting for information in a meeting or on a call. And the theoretical sort of non-viable scenario was needing that full 1 TB of RAM for maybe hundreds of thousands of dollars just to get it all into memory.
Precisely. Now, if a business owner back then considered trying to fit that entire 1 TB of data directly into RAM using that traditional architecture, they'd theoretically need 10,024 gigabit of RAM. At that time, the cost for that amount of high-performance server RAM would skyrocket to maybe around $12,000 to $15,000. And maybe, just maybe, you'd get a slightly better response time out of it, say 20 seconds instead of 30.
Okay, hold on. So if
Yeah.
I'm a business owner back then, you're telling me I can pay, say, $3,500 for a 30-second response, or I could pay $15,000 over 4 times the cost for a 20-second response. That's paying a massive premium for what seems like a marginal improvement of just 10 seconds. From a purely financial and practical perspective, most business owners would likely just say, no thanks, I'm happy enough with this configuration.
Absolutely. Or at most, they might consider investing maybe a little bit more, perhaps an extra $1,000 to increase their RAM slightly, maybe get it up to 384 GB or something, and shave off just a few seconds. Perhaps getting down to a 25 or 28 second response. But that huge jump from $3,500 to $15,000 for just a 10-second improvement, that just wasn't a compelling business case at all. It didn't make financial sense. And this bottleneck, this limitation, meant that real-time analytics or truly instant reporting was often simply impossible. Businesses had to rely on these slow, overnight batch processes or make decisions based on outdated data.
So what does this all mean then? If traditional databases hit this seemingly impenetrable wall of cost versus performance, and simply paying for more and more RAM wasn't economical, then why is everyone now flocking to these in-memory databases like SAP and Ada? What changed to make this whole approach viable? Okay, here's where it gets really interesting. So we've painted this picture of businesses hitting a wall with traditional databases, right? Kind of ceiling on performance versus cost. But then, as you mentioned earlier, a true revolution occurred. The in-memory database. What exactly is that, and how did it shatter that old trade-off we just discussed?
The fundamental shift with SAP HANA is right there in the name. It is an in-memory database. This fundamentally means that the entire database, both the database software itself and, crucially, all the critical business data, is designed to be stored and primarily processed in your physical memory, your RAM. This fundamentally changes the whole game. Because, well, if all your data is resident in RAM, then theoretically, your hit ratio should be 100%.
100%.
Right. No more going down to that slow hard disk for primary operations. No more constant data swapping back and forth. No more waiting for data to be pulled into memory before you can work with it.
That sounds absolutely incredible. But as we just discussed, that initial cost comparison of putting, say, 1 TB of data entirely into RAM seemed prohibitive. So how did this actually become viable? The answer must lie in something more than just, wanting to put everything in RAM, right? There must be more to it.
Absolutely. The viability of in-memory databases like HANA didn't just come from simply wanting to put everything in RAM. That initial cost comparison, as you said, did indeed make it seem almost impossible for a long time. The answer lies in a really powerful combination of significant recent advancements, both on the hardware side and perhaps even more crucially on the software front. These advancements together transformed what was once a theoretical desire into a practical and, importantly, cost-effective reality. Okay, so on the hardware side first, we've seen just incredible leaps in capability in just the last decade or so. Modern machines now feature profoundly powerful multi-core architectures in their CPUs. We're talking about processors with many, many cores, 16, 32, 128, even 256 cores, all working in parallel within a single server. This enables massive parallel processing of tasks. Instead of one core handling one calculation at a time, sequentially, you now have potentially hundreds of these mini processors working in parallel on different segments of your data, all simultaneously. This allows complex queries that might have once taken minutes to be processed in mere fractions of seconds. It's like going from a single-lane country road to a superhighway with hundreds of lanes all moving at once.
That's a huge difference from just a few years ago when even like dual-core processors were considered pretty cutting edge.
Indeed. And coupled with this massive increase in processing power, there's been a dramatic increase in affordable RAM capacities. It's now possible, quite routinely, to acquire servers with truly massive amounts of RAM. 1 TB, 2 TB, even more are becoming commonplace in data centers, and importantly, they're becoming increasingly cost-effective per gigabyte. This makes the whole concept of storing an entire large database in memory, which was once prohibitively expensive due to the sheer cost of the memory modules themselves, much more feasible, just from a pure capacity standpoint. And finally, a sort of silent but absolutely critical enabler was the fundamental shift from 32-bit to 64-bit address space on processors. Think of it like this. A 32-bit system had a much smaller address book for memory locations. It physically limited how much RAM it could practically recognize and use, typically just around 4 GB.
Right, I remember that limit.
A 64-bit system, on the other hand, dramatically expands that address book, allowing it to effectively tap into those truly massive RAM capacities we now see in servers. It effectively removed a major bottleneck that once restricted large-scale in-memory computing.
Okay, so bigger, faster hardware that can handle vast amounts of RAM and address it efficiently.
Yeah.
That's a huge part of the story. But you mentioned software innovations too, and that sounds crucial, right? Because just throwing more hardware at the problem, as we saw with the traditional database dilemma, wasn't really enough to make the jump economically viable on its own.
Exactly. While those hardware advancements provided the essential foundation, the necessary horsepower, HANA also introduced several groundbreaking software innovations that are, frankly, nothing short of brilliant. These are really the unsung heroes that make the seemingly impossible possible. They are what truly and dramatically alter that cost-benefit equation we talked about, and they're what really set HANA apart. They enable it to fit massive data sets into a manageable amount of RAM and then process them with unheard of speed. So let's dive into these ingenious software secrets. This is where the real magic happens.
Okay, yeah, this is where it gets really interesting, I think. Because HANA isn't just about throwing more RAM at the problem and hoping for the best. It's about incredibly clever software design that actively optimizes how that RAM is used. It's not just where the data is stored, but how it's structured and accessed, even within that fast memory, that makes all the difference. Is that right?
Precisely. Let's break down these critical software innovations that truly set HANA apart and allow it to achieve such breakthrough performance, and importantly, make that whole in-memory model economically viable after all. So the first major innovation is the dual capability for row store versus column store tables. Traditional databases almost exclusively primarily use what are called row store tables. This means that data is stored, well, row by row. For example, if you have an employee record, the employee ID, the name, the department, the salary, all of that information is stored together contiguously as one complete row of data. This structure is inherently write optimistic. That means adding a new complete record, a new row, is very efficient because you just append a new self-contained block of data at the end.
Okay, so if I'm adding a brand new employee to my human resources system, it just drops that whole new record in one go, all the different data points together, easy peasy.
Exactly. This is ideal for what we call transactional systems, where you're constantly adding or updating complete records, like processing individual customer orders one by one. However, HANA offers both row store tables and, quite uniquely for a major enterprise-grade database, column store tables. Now, in a column store, data is stored column by column. So all the employee IDs are stored together physically in one column structure, all the employee names are stored together in another, all the departments in a third, and all the salaries in yet another column structure. This approach is profoundly read optimistic. It's absolutely perfect for analytical queries and aggregations, things like summing up sales figures or finding average salaries, which, perhaps surprisingly, make up the vast majority of operations in many modern business systems.
Huh. That sounds kind of counterintuitive at first glance. Why would storing it by column be faster for reading and doing analysis?
Okay, consider this illustrative example. Let's say you want to find the sum of all employee salaries across your entire company, maybe thousands or millions of employees. In a traditional row store database, the system has to read through each entire row just to extract that single salary field. It reads the employee ID, then the name, then the department, then the salary. Then it moves to the next row and repeats this whole process for every single employee. Lots of wasted reading.
Right. Reading data doesn't even need for that specific calculation.
Exactly. But in a column store, to get the sum of all salaries, the system only needs to read the salary column directly. It doesn't have to touch or process any of the other data like names or departments at all. It can simply scan right down that single contiguous column of numbers and sum them up directly. This is significantly, often orders of magnitude, faster for these kinds of analytical operations, especially when you're dealing with massive data sets.
That makes perfect sense now. If you only care about one specific piece of data across millions of records, you're not wasting time sifting through all the other irrelevant data in each record. You're just pulling the specific column you need. Much more efficient. And to connect this back to you, the listener, just think about how you use most business systems today. You probably perform far more read operations, searching for products, generating sales reports, comparing supply chain figures, analyzing customer behavior, than you do direct write operations, like actually placing a single order or entering one new customer. HA optimizes brilliantly for this common use case where reading and analysis are absolutely paramount for getting insights quickly.
That's precisely why it's so powerful. And the flexibility here is key. Database designers can choose which type of table to create based on how the data will actually be used. Frequently updated, very transactional data might still go into a row store table for optimal write performance. But historical data, or data that is constantly being analyzed and reported on, would almost certainly go into a column store to leverage that incredible read speed. In practice, though, most tables in a typical HANA system are, by default, columnar, simply because the benefits for analytical performance are so profound and analytics are so central to modern business. Okay, the second major innovation, and this one is absolutely vital for making an in-memory database practical, is data compression techniques. As we established, RAM is expensive, right? Even with modern advancements making it cheaper, it's still far more costly per gigabyte than disk storage. So to drastically reduce the data footprint, the amount of space the data takes up, and ensure that even truly massive amounts of business data can fit entirely and economically into that expensive RAM, HANA employs some ingenious and highly effective compression algorithms.
Okay. So it's not just about having more RAM available, but actively making the data smaller so it actually needs less RAM in the first place. That sounds incredibly clever, and that seems to directly address that cost barrier we kept hitting earlier.
It is, and it's a complete game changer for the economics of in-memory computing. The core method, one of the most impactful, is called dictionary compression. Instead of storing repeated character strings over and over and over again, for instance, if you have the string North America sales appearing millions of times in your transaction data, or maybe the department name Basis department appearing 500 times in your employee data, SAP HANA assigns a unique integer value ID to that specific string. So North America sales might become, say, the integer 1, and Basis department might become 2. Then wherever that string North America sales appears in the data, the system stores just the tiny integer 1. Now think about the difference in storage space. Writing the characters NORTHAMERCASALES many, many times takes up a significant amount of space.
So lots of bytes for each occurrence.
Exactly, but writing the single integer 1 takes vastly, vastly less space. This technique alone can often shrink data by 50% or even more, just with dictionary compression, depending entirely on how repetitive your data actually is, which in business data is often quite repetitive.
Wow, that's a huge reduction right off the bat. If you're potentially cutting your data size in half, or even more, you're directly cutting your RAM needs in half, and therefore significantly cutting your hardware cost. That's massive.
It's absolutely massive. And beyond just dictionary compression, HI employs other sophisticated techniques as well. For instance, there's prefix encoding, which looks for common beginnings of words or strings within a column and stores them efficiently. There's run length encoding, which is great for compressing long sequences of identical values into just a small code. For example, in SAP, instead of storing array, it just stores 5A. And cluster encoding, which groups similar values together for better compression. The combined impact of all these techniques working together is profound. A 1 TB raw database, thanks to HANA's advanced compression stack, can often be compressed down to approximately 300 gigabytes, maybe even less when it resides in RAM. This fundamentally changes the RAM requirements, making it economically feasible to store your entire active dataset in memory, solving that core cost problem. The third key innovation is partitioning. This concept involves breaking very large tables, perhaps tables with billions and billions of records, into multiple, smaller, more manageable chunks or partitions. Retrieving data from these smaller, more targeted chunks is inherently faster than searching one single monolithic giant table. It's basically applying a divide and conquer strategy to your data.
So it's kind of like breaking a massive multi-volume encyclopedia set into several smaller, more focused volumes. So if you're looking for something specific, you only have to search the relevant smaller volume instead of the entire giant tome.
Exactly that. If you're looking for sales data just from the first quarter, the query only needs to search the partition containing the first quarter's data, completely ignoring the rest. Much faster. But Adatex partitioning is a significant step further with its multi-host installation capability. ADA allows you to install a single logical database across multiple physical servers or hosts, all connected by a high-speed network. Each of these hosts has its own dedicated CPU and RAM resources. When you partition a very large table, you can actually distribute those partitions strategically across these different physical hosts. For example, maybe January's data partition lives on host 1, February's data partition on host 2, March's on host 3, and so on. Now, when a query is run that needs data from multiple partitions, say, a query for the entire first quarter, can then leverage the combined computing power, the CPUs and RAM, of all three of those separate servers simultaneously.
Ah, so each server tackles its own piece of the puzzle in parallel.
Precisely. Each server can process its own chunk of the table in parallel, dramatically boosting performance for large queries and enabling truly massive scalability for handling enormous data sets that wouldn't fit or perform well on a single machine.
That's a truly distributed and parallel approach then. Instead of one super powerful machine trying to do absolutely everything, you have a coordinated network of powerful machines all working on the same problem at the same time, effectively dividing the labor. That sounds incredibly robust, especially for very large enterprises.
Yes. It significantly enhances scalability, overall performance, and even system resilience for those enormous mission-critical datasets. Okay, the fourth big software innovation is the elimination of aggregate tables. This is a really significant simplification of the traditional database architecture and, more importantly, a massive win for getting real-time business insights. See, in traditional systems, to perform fast sums, averages, or other kinds of aggregations on large data sets, database administrators often had to create and maintain what are called aggregate tables. These were essentially pre-computed summary tables. For instance, a separate table might be created just to store the sum of sales for each region for the last month, or maybe the total quantity of a specific product sold daily.
So if a sales director wanted to know the total sales for the Northeast region last month, the database wouldn't actually calculate it on the fly from all the raw sales data.
Yeah.
It would just look up a number that was already pre-calculated and stored in a separate aggregated table.
Precisely. And the problem with this approach was really twofold. First, it meant maintaining redundant data. You had all the raw, detailed sales data, and you had these separate aggregated sales data tables. This consumed more storage and definitely complicated data management and consistency. And second, and crucially, these aggregate tables could easily become stale, outdated. If new sales came in right after the last aggregation job ran, the aggregate table wouldn't immediately reflect that new information. It would be out of date until the next update cycle.
Which means your real-time data isn't actually real-time at all. You might be making critical business decisions based on yesterday's numbers, or maybe even last week's numbers, without realizing it.
Exactly. And in today's incredibly fast-paced business environment, that kind of latency, that delay in insight, is simply unacceptable for many companies. HANA's solution here is both elegant and revolutionary. Because of the unprecedented speed offered by its combination of columnar storage, powerful compression, intelligent partitioning, and multi-core parallel processing, it can perform those complex aggregations in real time directly on the raw detailed data as the query is run. There's simply no longer any need to create and maintain those separate pre-computed aggregate tables.
Wow, this isn't just some minor technical tweak. That feels like a genuine paradigm shift for business intelligence. I mean, imagine a large retail chain during a huge Black Friday sale. In the past, they might not know their true profit margins per product or their real-time inventory levels across all stores until maybe days later when all those aggregate tables finally got updated overnight. But with something like HANA,
They can potentially see real-time profitability per product, per store, maybe even every minute. They could immediately adjust pricing, reallocate staff to busy stores, or push targeted promotions based on live, minute-by-minute sales data. It's like the difference between driving your business by looking mostly in the rearview mirror versus having a real-time GPS system with live traffic updates, instantly rerouting you to the most optimal path based on current conditions. This immediate, unadulterated truth of your business operations, that's the real aha moment here, isn't it?
That's a perfect illustration of the business impact. This capability dramatically simplifies the overall data model. It reduces total storage requirements by eliminating all that redundancy. And most importantly, it ensures that your business insights are always based on current actionable data. Businesses gain the agility to make much faster, much more informed decisions. Okay, the fifth and final core software innovation we'll discuss today is something called Insert Only on Delta, and this is specifically designed to optimize writes for those columnar tables. Now, we've talked a lot about how columnar tables are amazing for reads, their read-optimistic nature, and how they accelerate analytical queries. But writing new data to a compressed columnar table can actually be relatively slow. This is because adding new data or updating existing data often requires decompressing some part of the existing compressed data, inserting the new data or modifying the old, and then recompressing that whole block of data again. This whole process can be quite computationally intensive and time-consuming.
Okay. So the very thing that makes them so incredibly fast for reading, namely the heavy compression, actually makes them potentially slow for writing new data. That sounds like a bit of a catch-22 if you're trying to use columnar tables for everything, including, say, transactional data that changes frequently.
It absolutely would be, if not for HANA's ingenious solution to this problem. To make columnar tables also write-optimized, HANA uses a clever dual storage approach within RAM. This effectively gives you the best of both worlds. You have what's called main storage. This holds the vast bulk of your existing, highly compressed data. This main storage is rigorously optimized for those lightning-fast reads and analytical queries we've been discussing. Then, alongside it, you have delta storage. This is a smaller, typically uncompressed temporary area within RAM where all new data insertions or any updates to existing data are initially written. Because this delta storage is uncompressed and specifically designed for rapid insertion, writing to it is extremely fast. It's optimized purely for writes.
Okay, so new data comes in really quickly and goes into this temporary delta holding area. But then how do you read the most current accurate data if some of it is in the compressed main storage and some of the newest stuff is in the uncompressed delta storage? It sounds like you'd always have to check two places.
That's where ANA's intelligence really comes in. When you execute a query to read data, A just seamlessly and intelligently reads from both the main storage and the delta storage simultaneously. It combines the results to ensure you always get the most current and complete picture of the data. The database engine handles all this complexity completely behind the scenes, so the user or the application doesn't even need to know or worry about where the data physically resides at that exact moment. If you're performing an update to an existing record, the updated version is also initially written to the delta storage, and the old version in main storage is simply marked as invalid or superseded. The real magic then happens periodically and automatically through a crucial background process called the delta merge.
The delta merge. Okay, what does that process actually entail?
During a delta merge operation, the data that has accumulated in that temporary delta storage is efficiently merged into the main compressed main storage. This process often involves sorting the data from the delta store, compressing it using those techniques we discussed, and then integrating it seamlessly into the optimized structure of the main store. Once the merge operation is complete, the data in the delta storage has effectively been moved, and a new, empty delta storage area is then created, ready to receive the next batch of subsequent writes. These merge operations are highly optimized and designed to run with minimal impact on overall system performance, often happening quietly in the background during periods of lower system load.
Wow. So HA is essentially constantly optimizing and reorganizing itself behind the scenes. It's ensuring that new data can be written very quickly into that delta area, and then it's seamlessly integrated into the high-performance compressed main storage later on. It really does sound like you get the best of both worlds, fast writes for your transactional data, and still blazing fast reads for all your analytical data, even in the same table.
Exactly. This clever mechanism ensures fast writes to columnar tables without sacrificing their exceptional read performance. It truly overcomes a fundamental challenge inherent in pure columnar storage and enables what's often called hybrid transactional analytical processing, or HTAB, all on a single unified platform.
So let's bring this all back together. What does all this mean for our initial cost comparison? That seemed like such a real roadblock at first, right? Where just buying enough RAM for traditional databases simply didn't make sense from a business perspective. But now, with all these ingenious innovations layered on top to the columnar store, the intense compression, the intelligent partitioning, getting rid of aggregate tables for real-time aggregations, and this clever delta merge process, how do the numbers, and more importantly, the value proposition look now? Has it really changed things?
Let's quickly recap that old scenario just to compare. With a traditional database setup, maybe we had 256 gigabytes of RAM trying to handle 1 TB of data that lived primarily on the hard disk. The hardware cost was roughly in the range of, say, $3,000 to $4,000, and you were getting a typical response time of approximately 30 seconds for those complex queries.
Right, and the theoretical, but basically non-viable scenario for those traditional databases was needing that full 1 TB of RAM, costing maybe $12,000 to $15,000 just to get the data into memory. And even then, only getting maybe a marginal 10-second improvement in speed. Not worth it.
Precisely. But now let's look at the new HANA scenario, factoring in all those software innovations we just walked through. Firstly, and perhaps most importantly, that 1 TB of raw business data, thanks to HANA's advanced compression techniques, can often be compressed down to approximately 300 gigabytes when it resides in RAM.
Wow, okay, so you don't actually need 10 to 24 gigabytes of RAM anymore. You'll need roughly 300 gigabyte to hold the same amount of business information in memory. That's a massive difference in terms of cost and just physical feasibility.
Exactly. So instead of needing that prohibitively expensive 124 gigabytes of RAM, you now only require around 300 gigabytes of RAM, maybe a bit more for overhead, to hold your entire active database comfortably in memory. Now, when you factor in the current market costs for that amount of high-performance RAM and the supporting server hardware, the estimated hardware cost for HANA system capable of handling that original 1 TB of uncompressed data comes in somewhere around, let's say, $4,500 to $500, and your response time. With everything operating directly from memory, leveraging those powerful multi-core processors, the efficiency of columnar storage, and all those clever software optimizations working together, you're looking at response times potentially around 20 seconds for those same complex queries, and often significantly faster down into single-digit seconds or even sub-second responses for many common operations.
Okay, so this raises the really important question now. If you're that business owner, will you move to HANA now? Suddenly, the math looks completely different, doesn't it? The entire value proposition seems to have shifted dramatically.
The compelling argument for businesses now becomes crystal clear, I think. For only a marginally higher initial hardware cost, maybe moving from, say, $3,500 for the traditional setup to around $5,000 for the HANA setup, you're getting a radical performance boost. You're going from maybe 30 seconds down to 20 seconds or potentially even less for the exact same complex queries. And this isn't just a numerical improvement on a stopwatch. It fundamentally changes what a business can actually do with its data in real time. It moves you from slow, after-the-fact batch process reporting into the realm of genuine real-time insights and decision-making. The total cost of ownership starts to look highly attractive when you consider not just the hardware, but the dramatic speed increase, the simplified data model, no more aggregates, and the sheer business value of getting those real-time insights immediately. It's no longer a questionable investment. It becomes a powerful enabler for competitive advantage.
Yeah, it's like finding a new car model that's only slightly more expensive than the old one you were considering, perhaps just $1,500 more. But this new one gets vastly better mileage, has maybe double the horsepower, comes packed with advanced safety features you never thought you could afford, and includes that real-time navigation system you desperately need for your commute. Suddenly, the choice becomes pretty obvious, doesn't it? This is why customers are migrating. That initial, seemingly insurmountable hurdle of it's just too expensive for too little gain has been completely dismantled by this combination of hardware progress and, crucially, those software innovations. Okay, but wait a second. You've emphasized over and over that HANA stores everything in RAM, in physical memory. And we know RAM is volatile memory. That means if the power goes out unexpectedly or the whole system crashes, is all that critical business data just poof gone? That sounds like a huge, completely unacceptable risk. Businesses simply cannot afford to lose their vital data like that.
That's a critical and very, very valid question. And it's something that any robust database system, especially one relying so heavily on volatile memory for its primary operations, must address comprehensively. What's fascinating here is how HANA ensures complete data integrity and persistence despite using that volatile RAM for its primary processing speed. You are absolutely right that RAM is volatile. Any data currently held only in RAM is lost if the power is removed or the system crashes. However, HANA employs robust and continuous mechanisms for data persistence. All committed data in HANA, especially after those delta merges we discussed have integrated changes, is regularly and automatically persisted, meaning it's safely saved down to the hard disk drive. This is referred to as persistent storage or the persistent disk layer.
So it's constantly writing changes down to the disk in the background, effectively keeping a permanent, safe copy of everything that matters.
Exactly. It's a continuous automated process. Every single transactional change, every data modification that gets committed by an application is first recorded sequentially in a transaction log, and that log is immediately written durably to disk. Furthermore, the main data files themselves are regularly updated on disk through a process involving save points. These are essentially consistent snapshots of the entire database state at a particular point in time, written safely to the persistent disk storage. This combination ensures that no committed data is ever truly lost, even in the event of a sudden crash. And it's important to clarify something about the compression again here. Those amazing compression techniques we discussed, like shrinking 1 TB of data down to maybe 300 gigabytes, that compression only applies to the data while it's actively residing in RAM. On the hard disk, for that persistent storage layer, the data size generally remains its original uncompressed size. So your 1 TB of logical business data is still stored as roughly 1 TB on the physical disk.
Ah, okay.
But hard disks are incredibly cheap per gigabyte by comparison to RAM. So storing the full uncompressed data there for safety and durability isn't really a significant cost issue. The major cost benefit of compression applies solely to fitting the data efficiently into that expensive and performance-critical RAM layer.
Okay, that makes sense. So the data is always safely backed up on disk, providing the crucial durability businesses absolutely need. But if the system does go down for some reason and the RAM inevitably clears out, what happens when you start it back up? Does it take absolutely forever to reload that potentially massive amount of compressed data back into memory from the disk?
Yes, that's another important point of consideration and a difference from traditional systems. When you start the HANA database, for example, after a planned system shutdown for maintenance or following an unexpected power failure, it must load all the necessary active data and database objects from that persistent hard disk storage back into RAM before it becomes fully operational. This is why HANA's startup time is typically longer compared to traditional databases. Traditional databases only need to load a relatively small portion of frequently accessed data into their RAM buffer cache at startup, as they primarily rely on the disk for the rest of the data anyway. HANA, by contrast, aims to load the entire active data set that was previously residing in memory back into RAM during startup. For a large multi-terabyte system, this loading process could take several minutes or potentially even longer for truly massive instances, depending on the size of the data and the speed of the persistent storage.
Okay, so it might take a bit longer to get going initially, maybe after a reboot, but once it's fully loaded and up and running.
Once it's loaded, the system operates with that near 100% hit ratio we talked about earlier, delivering that lightning-fast performance because everything needed for processing is already right there in memory. So to summarize that crucial point, HANA ensures your critical business data is always safely backed up and persisted to disk, providing the necessary data integrity and recovery capabilities that businesses demand. But its incredible performance magic comes from operating with that data almost exclusively in memory once it's loaded during startup. This is the true meaning of an in-memory database. Data is processed primarily from memory for speed, but it's always persisted safely to disk for reliability and durability. It truly provides the best of both worlds, carefully balancing that need for speed with the absolute requirement for data safety.
So, wrapping this all up, what does it all mean for the bigger picture? The term in-memory database, it really isn't just some technical buzzword that sounds futuristic or cool. It represents a profound and genuinely practical shift in how large-scale enterprise data is managed and, more importantly, utilized. HANA, as a prime example, combines those cutting-edge hardware advancements like powerful multi-core processors and the availability of massive, affordable RAM with truly ingenious software innovations. We're talking about things like columnar storage for blazing fast analytical reads, those powerful compression techniques that dramatically shrink the data footprint and directly reduce hardware costs, intelligent partitioning that allows for massive scalability across multiple servers, the revolutionary elimination of cumbersome aggregate tables enabling truly real-time insights, and that clever delta merge process ensuring efficient writes even to those read-optimized columnar tables. All of this comes together synergistically to deliver a level of speed and efficiency that was, frankly, once unthinkable in the world of traditional business data processing.
And if we connect this to the bigger picture, Ada truly exemplifies how critical thinking and innovative software design can fundamentally transform established paradigms. It really highlights that true performance isn't just about raw processing power or throwing more hardware at a problem. It's about how intelligently you organize, store, and access information. It allows for the kind of real-time insights that can genuinely revolutionize business operations, enabling companies to make faster, far more informed decisions, react to market changes almost instantly, and gain a tangible competitive edge that simply wasn't possible with older, disk-bound technologies. What was once considered a significant, almost unavoidable trade-off between cost and performance has been fundamentally re-engineered by these combined hardware and software advancements, making real-time business not just a goal, but a practical reality for many organizations today.
This deep dive has really shown us how a strategic blend of hardware evolution and sheer saucer ingenuity can overcome significant, long-standing challenges. It's transformed what was once seen as an illogical or overly expensive investment into an essential, increasingly cost-effective tool for modern enterprises that are striving for agility and the power of real-time decision-making. And just as a final provocative thought for you, the listener, to maybe mull over, given how much more efficient these in-memory databases clearly are for processing vast amounts of data incredibly quickly, what other areas of our daily digital lives, maybe beyond just enterprise software, could be fundamentally transformed by this kind of technology? Areas where we don't even realize we're currently waiting on slow data access behind the scenes. Imagine, for example, how much faster data access could potentially change real-time analytics in professional sports coaching or broadcasting, or the precision and maybe the instantaneity of personalized recommendations you get on your streaming services or shopping sites, or even accelerating the speed of complex scientific research that works with massive, ever-growing data sets, like in genomics or climate modeling. What possibilities stand out most to you, hey?